Okay, students, let us continue the class buffer solution. In this session, I am going to derive an important equation, that is the pH of a buffer solution, that is the Anderson equation. Okay, that as I already mentioned, this is a very important equation that may be asked for the examination. That is, now I am going to derive the pH of the acidic buffer. Okay. Now you take a typical acidic buffer. Okay, you consider a typical acidic buffer like acetic acid and sodium acetate. In this buffer solution, as I have already mentioned, there is an equilibrium of acetic acid that exists with its own ion, that is acetate ion and H plus ion. Okay, because of its feeble dissociation. That is the ionic equilibrium of acetic acid. And there is another equilibrium, that is a fully dissociated equilibrium that exists between the salt, that is sodium acetate, with this ion, that is sodium ion and Na+. Okay, let us consider the equilibrium of acetic acid. That is very important. When we apply the law of mass action, as I already mentioned, the case of ozone dilution law, we have the constant, that is dissociation constant Ka of the acetic acid is equal to the concentration of acetate ion into the concentration of H plus or hydronium ion divided by the concentration of acetic acid. That is expression for Ka, the ionization constant of acetic acid. On rearranging this equation, we have to write the expression for H plus or hydronium ion. That is, the concentration of H plus or hydronium ion is equal to Ka into the acetic acid concentration divided by the concentration of acetate ion. Taking the logarithm, that is, log H plus is equal to log Ka plus log acetic acid by acetate ion. The term is 1, that is log acetic acid divided by the acetate ion concentration. Okay. Next, as you know, acetic acid is a weak acid. Its dissociation is very small. Also, it is further suppressed by the presence of the acetate ion. Hence, the concentration of the acetic acid at equilibrium can be taken as its initial concentration. Okay, the concentration of acetic acid can be taken as equal to the initial concentration of the acetic acid, that is the concentration of acid. Then, the concentration of acetate ion can be taken as equal to the concentration of the salt, the initial concentration of the salt, because it is fully dissociated. Okay, then changing the sign throughout, mathematical work, that is minus log H plus is equal to minus log Ka minus log concentration of acid by the concentration of the salt. Okay, by the proper substitution, we have the term acetic acid become the acid concentration and the acetate become the salt concentration. Now already you know minus log H plus, that is equal to pH. Okay, minus log and minus log Ka is pK. On reverting the equation, we have minus log H plus is equal to minus log Ka plus log salt by acid. Okay, you just reverse the last term so that the minus sign become plus sign, the logarithm term. That is now become plus log concentration salt by concentration of the acid. So pH minus log H plus is pH equal to minus log K is pK plus log concentration of the salt divided by the concentration of the acid. That is the famous Anderson equation. That is by simply knowing the concentration of the salt and the concentration of the weak acids and knowing the pKa value of water. Okay, it is minus log Kw. We can possible to calculate the pH of a acidic buffer solution. Okay, I am giving you an assignment in this fashion. Okay, you have to derive Anderson equation for pOH and hence pH of a basic buffer, taking ammonium hydroxide and ammonium chloride as a typical example. Okay, you please go for the derivation. Okay, note that pH is equal to 14 minus pOH. You first derive pOH and then come to pH as 14 minus pOH. So it's an assignment to you. Then please try to work out some problem in connection with the pH. Okay. The problem are, you have to calculate the pH of 0.001 molar HCl. Okay, 0.005 molar sulfuric acid. You please look at the equation, H2SO4 giving 2H plus SO4 2 minus, remember. So 0.005 molar sulfuric acid give 2 into 0.005 molar H plus ion. So the effective concentration of H plus in the solution is twice the molar concentration of sulfuric acid. So you don't make a mistake. The concentration of H plus ion in sulfuric acid is 2 times its initial or molar concentration. The next 0.01 molar NaOH. You calculate pOH then pH. The next, calculate the pH of 0.1 molar acetic acid at 25 degrees Celsius. It is a weak acid. It is a weak acid. So you are provided with the Ka of acetic acid at 25 degrees Celsius as 4.9 into 10 raised to minus 8. Okay. It's a problem involving 3 steps. You cannot directly take the pH of this system because it's a weak acid. The initial concentration of the acetic acid is not the concentration of H plus ion in the solution. So please careful. The step number 1, calculate alpha of acetic acid using the equation 1, that is alpha is equal to square root of K by C, that I already mentioned to you. First you have to calculate alpha, the degree of dissociation of acetic acid, by knowing its Ka and initial concentration C, that is equal to alpha is equal to square root of Ka by C. Okay. Then next step 2, calculate the hydronium ion concentration or H plus ion concentration in the solution, aqueous solution. Okay, using the equation, that is H plus or H3O plus is equal to C alpha. Okay, it is a product of initial concentration and degree of dissociation. Okay, C alpha moles per liter. Once H3O plus or H plus is obtained, then step number 3, calculate pH using the familiar equation. pH is equal to minus log H3O plus. That is all. The answer now comes to be 4.15. Please check. Then finally, the salt hydrolysis in this connection. As already all of you know, a salt is a neutralization product of an acid and a base. Okay? It is a neutralization product of an acid and a base. So what happens when such a neutral salt dissolves in water or interacts with water? That is the problem of hydrolysis, or that is a discussion behind the hydrolysis. One may expect that when a neutral salt interacts with the water, okay, normally one supposes that the solution may be neutral always. Okay, it may be our thinking or notion. aqueous solution of a salt may be in most cases neutral. That is our thinking. But actually that is not the case always. Okay. We have 4 different types of salts I wish to mention. That is, one is the salt of strong acid and a strong base like NaCl. Salt of a strong acid and strong base like NaCl. Strong salt acid and strong base. Okay, both are strong and typical salt is NaCl. NaCl. Okay. And second is the salt of weak acid and a strong base. Weak acid and a strong base like sodium acetate. Like sodium acetate and sodium carbonate. And third is the salt of weak base and strong acid. Example, ammonium chloride, aluminum chloride, ferric chloride, etc. And finally, the fourth is the salt of weak acid and weak base. Both are weak. Weak acid and weak base. Example, ammonium acetate. Okay. As all of you remember, what happens to this salt when dissolves in water? Okay. As all of you know, what is hydrolysis, salt hydrolysis? The interaction of the cation and anion of the salt with water molecule producing acid and base in the aqueous solution. That process is called hydrolysis. So remember, due to this process, both acid and base are produced in the aqueous solution by the interaction. The aqueous solution may be acidic or it may be basic or neutral depending on the strength of the acid and base that is produced during the hydrolysis. Okay? It may be acidic or it may be basic or it may even neutral depending on the strength of the acid and base that is produced during the hydrolysis. The first category, that is the aqueous salt solution of strong acid and strong base that I have not mentioned here, that is NaCl like, okay, NaCl, that is a sort of strong acid and strong base. They do not undergo hydrolysis at all. They do not undergo hydrolysis at all with water. Instead, they get dissociated and undergo a process called solvation or hydration. Okay, that aspect is different, but at the solution is neutral. It is not the hydrolysis, it is the process of dissociation and hydration. Okay, I am not going to discuss it here. It is not at all undergoing hydrolysis, but the solution is neutral. At the solution is neutral. Then we have to discuss the 3 other cases. The connection with hydrolysis. One is the hydrolysis of the salt solution of sodium acetate. Okay, sodium acetate, that is a weak acid and a strong base. Okay, that solution, the aqueous solution of such a salt is basic in nature. Okay, such a solution is basic in nature. How it happened? Let me explain. Let me explain the mechanism. That is, sodium acetate, when dissolved in water, interact with it, forming a weak acid, acetic acid, and a strong base, NaOH. As you know, acetic acid is a weak acid and it is feebly ionizing, and hence the concentration of H plus ion is low in the solution. While the NaOH is a strong base, okay, it is a strong base, it is fully ionizing and OH minus ion concentration is high. The OH minus ion concentration is much higher than the concentration of H plus. Okay. Therefore, the solution is basic or alkaline in nature. Okay. Then the the case that is of the salt of weak base and a strong acid like ammonium chloride. So it is acidic in nature due to the hydrolysis. Due to the hydrolysis, the aqueous solution is acidic. Let me explain. Okay. No, I am not going to explain. Please try to explain the nature or the aqueous solution of ammonium chloride and ammonium chloride and that of ammonium acetate. So you have to carry out or you have to work out two assignments. One is that of ammonium chloride. I want to say it is acidic in nature. The aqueous solution of ammonium chloride is acidic in nature due to hydrolysis. And the aqueous solution of ammonium acetate is neutral. Okay, it is neutral due to the hydrolysis. You please explain how it happens by explaining the mechanism as I explained in the case of the that is sodium acetate. Okay, please try to explain it. You consider it an assignment. Okay, now I am going to finish or stop the class. So I wish you all success in the examination, and I hope that I have fully finished the chapter. Wish you all good luck. Okay. Thank you very much for your patience in listening me. Okay, dear students.